Hi, everyone. So welcome back to the HoTT-UF workshop in 2020. Today, we'll have Roberta Bonacina tell us about a proof theoretical semantics for homotopy type theory. And I just want to remind everyone before we begin that we want to keep questions during the talk to a minimum so that the author can, or the talker can get through her talk. All right, Roberta.
Thank you very much. So today, no, it's not. Okay. I'm going to present this work, which is based on, this semantics for Martin Love type theory, the fragment which comprehends the structural rules and the dependent product. This semantics is described in details in my PhD dissertation. So the semantics is oriented, the idea is that we wanted to use it to study some proof theoretical properties of the system and to have a completeness and an easy to use classifying model as done by Abel, Cocan, and Dibier for per models. So the point here is that we did not mean to provide a meaning to the system. And so for this reason, there are two consequences, which are that comparing our semantics with others may not be so natural because just because they have different aims. And also because of that is justifying the fact that there are no natural models apart, of course, the canonical one. So our semantics uses one category theory, and it is based on a couple of ideas. We identify using isomorphisms equal terms. Here with equal, we mean through judgmental equality, not propositional one. And we see types as transformations. And we formalize this notion using functors. So given a theory, we define a model for it as a category together with an interpretation for which every derivable expression can be interpreted. Here we have a visual idea. We have a first category C, which is a preorder category with an initial object, which is deputed to interpret context. And the initial object is the empty context. And whenever a context D extends another context C, we have an arrow from C to D. Then we interpret a judgment in a context in the slice category over it. So both the term in context, small a, and type in context, big A, are interpreted in object in the slice category, while the judgment itself is interpreted as an arrow from the type to the term. And weakening is easily interpreted just by using the properties of slice categories. Indeed, the interpretation of the judgment in a bigger context is exactly the same, while the interpretation of the term and type in context can be obtained from the one in the previous context just by composing with the arrow from the two contexts. So this is the main idea, and to formalize it, we needed to introduce some elements to interpret the different expressions. So we have, as I said, the category C, which models the context, with the initial object, which is the empty context. Then we have, for each universe, an object small ui in the slice category over the empty context, which can be extended to interpret universes in every context just by composing with the unique arrow from the empty context to the other context C. Then, given a context and a type, which we can model the extension of the context with a variable of type A, with a certain arrow new, and the variable itself, we interpret the variable itself with another arrow key. Then, focusing to interpret the dependent product, we have three functors, which are fpi, ipi, and epi, which model the formation, introduction, and elimination rules, respectively. And at the end, an auxiliary functor S, which is used to interpret substitution. And it is defined as a composition of the introduction and elimination functors, which is what is naturally suggested by the computation rule for the product. This is an example of the rules for to interpret the formation of the dependent product. So this is what we require to the functor of pi. It is indeed a family of functors indexed by an object which interprets the context and another object which is the domain of the dependent product. And we require that it goes from a subcategory of the slice category over the extended context into a subcategory of the slice category of the context, the smaller one. Then we require that it is stable with respect to context extensions and that it respects isomorphisms and preserves universes. And you can read the detailed requirements on the slide. And at the end, we want fpi to be conservative. Actually, what we needed to interpret the elimination rule was that the injectivity of pi. But we required the conservativity because it's a nicer categorical property. And so we have other requirements for the other rules and for the basic system. You can find them in my PhD dissertation. And we prove that our semantics is sound and complete. So the structure of the completeness proof uses a canonical model. So we define the syntactical category. We show that it is a model, the canonical one. And then we have that if an expression can be interpreted in every model, then it can be interpreted, of course, in particular in the canonical one. And so by construction, it has to be derivable. We also prove that the canonical model is classifying. So we can reach from it every other model using the functor which preserves the interpretation. Now let's give a closer look to the syntactic category. Considering a theory T as the set of derivable judgments, we have the set of objects, which is obtained by having an object for each equivalence class of context. Here, the equivalence relation is done by the permutations of the variables, the typed variables. And for each judgment, we define an object for the terming context, which is a couple, having as the first term the object itself, and as the second one, the equivalence class of the smallest subcontext of gamma in which the term can be defined. Then the pairs of objects are seen, of course, as arrows. So the first term is, the first element is the domain and the second one is the codomain. And we define composition in the natural way. And so from that we can obtain the set of arrows. And we define it as, we define inductively. And we have an arrow for context extension. So where the first element is the equivalence class of the context and the second one of the context is extended with the new variable. Then we have an arrow relating to contexts which are equivalent again, but this time with a less strict equivalence relation, which consider also the fact that into context there may be judgmentally equal types. Then we have an arrow, which is repeated to interpret the judgment, which maps, which is from the interpretation of from the typing context to the terming context, and another one which goes from the terming context to the smallest context in which it can be defined. Then we have another arrow for repeated to interpret judgmental equivalence, the judgmental equivalences. So from the it relates, it says an isomorphism relating the two judgmentally equal terming contexts. And then, of course, we have the identities and composition. So we can finally define the syntactical category, which has the object and the arrows, which we have just defined. And it has prefunctors deputed to interpret the formation, introduction, and elimination rules. And finally, another object which is deputed to interpret variables. So now we can define the canonical interpretation. And we interpret each context in the unique arrow from the empty context, so the initial object in C, to the equivalence class of the context itself. Then each terming context is interpreted as the arrow from the terming context to the equivalence class of the context. The judgment is interpreted, as I said, as an arrow from the typing context to the terming context, and each equivalence judgment is interpreted as the arrow from the two equivalent terming contexts. So we use this fact and the canonical model to prove a couple of results, which to stress the proof theoretical nature of our semantics. And the first result says that pi is injective. So if we have the product pi x of type A dot B, which is equivalent to another product pi x of type C dot D, we can prove that A and C are equivalent in the judgment gamma, in the context gamma, and also B and D are equivalent in the context gamma extended with the x of type A. So in the we have that in the classifying model, our hypothesis become that the interpretation of the two dependent product type in context are isomorphic. And so just by substituting by definition of interpretation, also the two F pi functors applied to the context to the interpretation of the two domains and the interpretation of the two codomains has to be isomorphic. But we require that F pi is conservative, and so also the two interpretation of the type B with the context gamma x of type A and the type D with the context gamma x of type C are isomorphic. And so by definition of the classifying model, we have that also the two contexts, the interpretation of the two contexts are isomorphic. And so in particular, the interpretation of the two terms in context A and C are isomorphic, which is the first conclusion. We obtained the second one because since F pi respects and reflects isomorphisms, it follows that also the interpretation of B and D in the same context gamma x of type A are isomorphic. And so by completeness, our thesis follows. The second result is that in no case a universe is judgmentally equal to a product type. So suppose by contradiction then that it is, we have that the two interpretations of the terms in context are isomorphic. But again, F pi is conservative. And so computing its inverse to the interpretation of the dependent product, we obtain that the interpretation of B in the context gamma x of type A. And so we obtain that the functor f pi has to be defined on the interpretation of the universe. And applying its inverse, we obtained that the inverse has to be equal, the inverse f pi to the -1 applied to the interpretation of the universe has to be equal to the interpretation of a certain terming context C, with the context again gamma x of type A. But we get that if we apply the f pi functor to this object, we obtain the interpretation of a certain product type, which has to be exactly equal to the interpretation of the universe. But if we regard this result in the classifying model, this imposes that the dependent product and the universe has to be literally equal, so with exactly the same writing, which is false. And from that we can obtain our statement. So we have seen now the results for a fragment of Martin-Löf type theory, but we can actually extend the semantics and so the seen results to a large fragment of homotopy type theory. To do that, we defined a generic syntax for the inductive types, which has all the canonical ones as instances, and also a generic syntax for a subset of the higher inductive types, which we call the one higher inductive types. All those rules and also the axioms of univalence and function extensionality are written in the language of Martin-Löf type theory plus the dependent product types. And our one higher inductive types are a subset of the higher inductive types, in which the higher constructor of a certain type is limited to the first level. So we can have only a higher constructor of type equal tau. So for example, the circle is a one higher inductive type, while the torus is not. And so we believe that the semantics can be extended to every single higher inductive types, but we will need to do that in a generic syntax for comprehending all of them, and we didn't obtain that in my dissertation. But yeah, I think that having it, we could extend the results. So just the last slide with the bibliography. Thank you for listening.
Okay, thanks a lot. So now we'll have some silent applause.
Thank you.
And does anybody have any questions? So I have a question first. So if you think about other simple dependent type formers like sigma or the identity types,
yes,
are you including them in
yes,
this inductive,
yes,
non-higher but inductive type?
Yes.
So you would know how to handle those.
Yeah.
And I also wanted to ask how this interfaces with, like, if at all, with comprehension categories and those kinds of notions of model.
I don't know.
Okay, any other questions?
Maybe you said that, but can you remind me, what are the morphisms in your category of context?
They are just the arrows from the smaller context to from the equivalence classes of the context to the equivalence class of the bigger ones, and isomorphisms between equivalent contexts in the. We have two notions of equivalences with the contexts. The first one is just related to permutations, while the second one also takes care of the equivalence of types, which may appear inside the context. So we identify the first one, the first case, while just the interpretation of equivalent context in the second with the second notion are isomorphic.
So there's another question getting by chat from Steve
Yeah.
Audi, and he asks, have you given semantics for identity types?
They're just seen as, well, I should have, yeah. This is an example of how I write the rules, the formation and introduction rules of identity types. And they are interpreted as, again, as functors. Similarly of how we have seen for the formation of pi.
Okay, any other questions? All right, so let's thank Roberta again with some silent applause. Thanks.
Thank you.